At sea, the forces of nature are entirely unforgiving. During a violent storm, waves can reach the height of buildings, and winds can overwhelm even the most powerful ship engines. The physical and economic scale of the danger is immense. Megaships like the CSCL Globe carry up to 240,000 tons of gross cargo. When fully loaded with technology and manufactured goods, a single vessel represents an investment of over $1 billion. If those engines fail, or the sea overpowers the ship's propulsion, the safety of the crew and the survival of that billion-dollar cargo rely entirely on a single point of connection, the anchor chain. This creates a critical engineering bottleneck. A factory must construct a continuous chain stretching 500 meters, where a microscopic flaw in just one link results in the catastrophic failure of the entire system. To withstand the most brutal natural conditions of the open ocean, the steel must first survive an uncompromising gauntlet of artificial forces inside the factory. The process begins with solid 100-kilogram bars of high-quality steel alloy. These are fed into an induction furnace, where a magnetic field heats the metal's core until it reaches a malleable 1600 degrees Fahrenheit. Once glowing red-hot, a hydraulic press molds and bends the ingot into a precise U-shape. Before the metal cools, an operator manually threads this open link through the last finished loop on the chain. To close the loop, the factory uses resistance butt welding. Powerful copper electrodes clamp onto the joint, applying intense electric current. The steel's resistance generates extreme heat, melting the metal at contact points. This diagram shows the result of that current. The separate ends undergo a molecular fusion, weaving the steel structures together into a single, indivisible piece that is as strong at the joint as it is anywhere else. The welding process leaves behind excess solidified material called burr. In seconds, high-pressure hardened steel jaws are forced against the joint, and the burr is sheared off to create a smooth, uniform surface. This molecular fusion ensures that under extreme tension, the joint will not become a weak point in the chain. When an anchor chain is subjected to 240,000 tons of tension, an empty metal loop faces a physical risk. The sides can collapse and crush inward. Looking at the interior of these links, you can see a solid bar fixed across the center of every loop. This internal support, known as a stud, acts as a skeleton for the link. It prevents inward deformation and multiplies the overall resistance of the chain against the weight of the ship. Securing this piece requires an ingenious use of temperature. While the link is glowing hot, an operator inserts a cold stud into its center. As the hot outer link cools, the metal naturally contracts and shrinks. This thermal contraction crushes down onto the ends of the stud with thousands of tons of force. By leveraging the basic laws of thermal physics, the factory creates a tighter, more permanent lock than could be achieved with mechanical tools. While the chain links provide the length, the bow shackle provides the connection. This is the ultimate joint between the entire chain assembly and the anchor itself. Shaping these components requires immense pressure. A powerful press strikes a 130-pound steel ingot to forge the shackle pin, to compact its internal structure, improving the mechanical properties needed to bear the ship's full load. This forging process creates a metallurgical challenge. While the steel becomes incredibly hard, it also becomes dangerously brittle. If the shackle cannot flex, a sudden impact from a wave could cause the metal to shatter. To solve this, the piece undergoes a 3-stage heat treatment. First, it is heated to over 1,500 degrees Fahrenheit. This diagram illustrates how the heat expands the internal structure, allowing carbon atoms to distribute evenly throughout the metal. Next, the shackle is plunged into a specialized oil bath. This rapid shock cooling locks the steel into an ultra-resistant, rigid form called martensite. Finally, the steel is tempered. By baking the piece at a lower temperature, engineers eliminate the brittleness and trade it for essential toughness, allowing the metal to absorb stress without cracking. To protect the steel from salt water, the finished shackle is immersed in a $100,000 bath of molten zinc, which bonds to the metal to form a corrosion-resistant armor. Carefully managing this molecular dance is the only way a single piece of metal can safely secure a massive maritime operation. Theoretical engineering only goes so far. Before a chain is deployed, it must survive factory tests designed to be more punishing than an actual ocean storm. Testing begins with microscopic inspections. Technicians use magnetic particles to search for subsurface fractures that are entirely invisible to the human eye. Next, the metal is subjected to impact tests. Heavy pendulums strike steel samples to ensure the material can absorb sudden, violent shocks without snapping. The ultimate verification is the tensile test. The full chain is locked into a massive rig and pulled with up to 2,400 tons of force. Each link and weld must withstand this tension without any permanent deformation. For final protection, the chain is immersed in a water-based asphalt coating. This material remains flexible in freezing sea temperatures, providing a durable barrier against corrosion. Passing this relentless gauntlet is the only way to certify that 500 meters of steel contains no structural weaknesses. From the factory floor, these verified chains are transported to global ports. They are loaded onto the massive vessels that drive international trade. The responsibility resting on these chains is enormous. A single megaship carrying hundreds of thousands of tons of cargo represents an investment of over $1 billion. In a world of digital logistics and high-speed trade, the physical reality of moving goods remains unchanged. It depends on the uncompromising strength of the steel required to hold these ships in place. The stability of global trade and the safety of crews at sea depend on these points of connection, physical steel engineered to withstand the relentless movement of the ocean.